Good morning to all of you. So, in the last class, I told you about how do we draw the ellipsoid, and then the change in shape, orientation, or size of the ellipsoid can happen during the vibration. So we try to follow that, and based on the variation in size, shape, or orientation of the ellipsoid, you can say whether there is change in polarizability very close to the equilibrium point, right? So ellipsoid was something as a three-dimensional uh, entity, three-dimensional thing, geometrical entity, which can you can ये कैसे आता है? It is when you draw an ellipse and उसको एक बार मेजर एक्सिस और एक बार माइनर एक्सिस के अलॉन्ग उसको रोटेट कर दो थ्री डायमेंशनल स्पेस में जो एक कुछ बनेगा वो उसको एलिप्सॉइड कहते हैं. सो ऐसा कुछ एलिप्सॉइड होता है और इसकी ज़रूरत इसलिए पड़ी कि ये जो पोलराइजेबिलिटी है इट इज़ नॉट अ स्केलर, नॉट अ वेक्टर, इट इज़ अ टेंसर. ठीक है, और टेंसर को सिर्फ आप एरोस ड्रॉ करके नहीं दिखा सकते. इट हैज़ ऑल्सो हैज़ अ शेप, इट जनरेट्स अ शेप. So it is for such quantities you have to draw a three-dimensional thing just like this to show the three aspects: this uh, the magnitude, the direction, and the shape. So the shape of polarizability ellipsoid is drawn as 1 by alpha is the scale that you take. So in the direction where there is largest polarizability, the axis would be drawn as the smallest, and on the along the direction in which you have the lowest polarizability, the axis would be longer. So this is the axis of low polarizability, and this one हाई पोलराइजेबिलिटी का ये वाला होगा. इस तरह से करके ड्रॉ किया गया था. तो दिस समथिंग यू कैन, सो द व्यू इज लाइक दिस कि एक बार प्लेन में आप देख रहे हो, एक बार परपेंडिकुलर टू स्क्रीन, और इलेक्ट्रिक फील्ड आपने अप्लाई किया. सो you will have maximum polarization along this direction, and if you rotate the molecule like this, then the polarizability will appear to be, ellipsoid will look like this. So based on that, I told you that for all linear molecules, you have the shape of ellipsoid is like a tangerine. Okay, so all have general shape. They only differ in relative sizes for such linear molecules. Okay, so and this was the case. So these are the shapes of various ellipsoids. Water molecule placed in three different ways. You can have the ellipsoid drawn like this. And so we also discussed what is the fundamental thing that determines Raman activity. So this is the thing: change in polarizability during vibration. Del alpha by del q should not be equal to 0. It should be a non-zero value. So two examples graphically, if I follow alpha versus q is the coordinates, vibration coordinates. So slope at the equilibrium point, the mean position, q is equal to 0. Look at the slope at the mean position here. So you draw a slope and find the value that gives you a clear idea whether it will be Raman active or not. So here d alpha by dq is non-zero, but here d alpha by dq is 0. Okay, so that's why we call this one is inactive, this one. So this kind of profile if you obtain for polarizability variation, you can clearly say what is. So now we also looked into the how does the polarizability ellipsoid varies, कैसे चेंज करता है वो हमने ऑब्जर्व करने की कोशिश किया. सिमेट्रिक स्ट्रेचिंग, सिमेट्रिक स्ट्रेचिंग में बॉन्ड जब स्ट्रेच कंडीशन में होगा तो पोलराइजेबिलिटी ज़्यादा होगी, यू कैन क्रिएट मोर डिस्टॉर्शन ऑफ द इलेक्ट्रॉन क्लाउड। और ऐसा इसलिए हो रहा है कि जैसे स्ट्रेच कर रहे हैं इलेक्ट्रॉन डेंसिटी फैल जा रही है, इट इज स्प्रेडिंग आउट टू अ लार्जर एरिया, it is less tightly held by the nuclei, and so when you apply electric field, distortion produced will be more. So see, the ellipsoid is smallest because ये 1 by alpha का scale है, 1 by under root alpha is the scale, so that is your giving you rise to this kind of axis. Okay, so because of that, and when it is in normal situation under equilibrium, mean position, you have the shape is same but it has become larger, and then when it is compressed the ellipsoid is the largest in symmetric setting. So least polarizable visibility. During the vibration the polarizability is changing continuously from left to right on your screen. So large ellipsoid, okay, inverse thing. So there is changing, so because of the size is changing it should be Raman active. One of the aspect, तीन में से कोई एक चीज चेंज होना चाहिए ellipsoid का. So here there is change in ellipsoid size. Bending में जब देखते हैं तो you will realize that it has, this is the mean, start with the mean position, then it is moving towards the becoming this इधर मूव कर रहा है डायरेक्शन में, so that is your bending motion, and इसमें इधर की ओर मूवमेंट हो रहा है सारा like this from the mean position. So that kind of movement, if you see, the changes the shape of the polarizability ellipsoid, and because of this it will be Raman active. And the third one is the asymmetric stretching mode. इधर वाला छोटा हो रहा है, compress हो रहा है, इधर वाला elongate हो रहा है. On this extreme reverse is happening. Okay, so the orientation in this case, the mean as compared to the mean position, the ellipsoid is changing its orientation. So again, so this is about the directionality of the polarizability. तो polarizability का direction change हो रहा है, again it will be Raman active. So all the three, so we have 3 vibration in water molecules and all 3 are Raman active, but the Raman activity is due to the 3 different things. In the polarizability का 3 अलग अलग aspect है जो change हो रहा है. एक में size change हो रहा है polarizability ellipsoid का, दूसरे में shape change हो रहा था, और तीसरे में जो अभी हमने देखा it is the change of the direction. So any of the 3 aspect अगर change कर रहा है तो आपका Raman active होगा. ये एक चीज है. और the same thing is written over here, I don't have to repeat that. Asymmetric stretching. So all the 3 what we have learned, a vibration, at least one aspect of the polarizability ellipsoid is changing and all are Raman active. So in the third one we have seen asymmetric stretching, size and shape remain constant but the direction of major axis is changing. We just seen that major axis is changing, you can clearly see this. So to visualize this thing, let me just go back. I will show you one interesting stuff over here. So this is what, एक मिनट थोड़ा सा zoom कर दूं. So let's take the water So you want to, water is here. This is your symmetric stretching. सिमेट्रिक स्टिचिंग, और ग्रीन वाला देखिए, वो आपका पोलराइजेबिलिटी एलिप्सॉइड है. दिस इज योर पोलराइजेबिलिटी एलिप्सॉइड. एंड सी ड्यूरिंग द सिमेट्रिक स्टिचिंग हाउ the green ellipsoid is changing its shape. So, and at the same time, so that is so because of the change in ellipsoid size, it is Raman active. And because if you look at the dipole changes, that is also drawn on the right hand side, and because of this it is IR active. Now check the other one, bending mode. This is the bending, and see, correlate the thing. If you are looking very carefully, see the change in ellipsoid, the grain, and the vibration that is happening. This is bending mode, and the shape of the ellipsoid is changing. Polarizability ellipsoid changes its shape during the bending, and because of that it is Raman active. So the dipole moment, there is also change in the dipole moment during the vibration, and so it is also Raman active, IR active, sorry. Third one that we just discussed, the animation for asymmetric stretching. देखो एक छोटा हो रहा है तो एक बड़ा हो रहा है, इधर elongate हो रहा है. So during this whole thing, this is the correlated motion of the visualization of how the ellipsoid, polarizability ellipsoid changes. So here it is, this, the shape is constant, the size is constant, but there is only change of the orientation, the direction is changing. So this is your visualization of what happens in case of water. Similarly, we can go back to the next part. For okay, so this was our, so this is the spectrum obtained for Raman spectrum of water, which you can see the three peaks, symmetric stretching, asymmetric stretching, and the bending mode. For CO2, in case of CO2, if we look at the symmetric stretching, the shape of ellipsoid is drawn like this. So देखिए, along this direction you have largest electron density, you can bring about the largest change in largest distortion of the electron cloud. So polarizability ज़्यादा है तो देखिए छोटा सा बनाया गया. एलिप्सॉइड उल्टा चलता है. एलिप्सॉइड में जिस तरफ पोलराइजेबिलिटी ज़्यादा होगी उसका एक्सिस जो लेंथ है वो छोटा हो जाएगा एलिप्सॉइड में. ठीक है. एंड so this is the thing. So as it is stretched, this is the stretched, this is the mean, and this is the compressed or contracted, whatever you may say, thing. So देख रहे हैं polarizability. So there is a change in shape, a change in size of the polarizability ellipsoid. So जब आप imagine you are following it with the change in coordinates, so ऐसा ग्राफ आएगा near the, at the, as alpha tends to 0, when at the mean position, if you draw the d alpha by dq, the slope, it is positive. So this is your, this is Raman active. So this is Raman active because d alpha by dq is not, is which is showing here, d alpha by dq here is positive, coming out to be positive, non-zero value. Okay, then you also have the bending mode. अब आप पिक्चर देख के समझ सकते हैं. If you are drawing ellipsoid, see very carefully. This is the mean position. Always draw mean position, the original ellipsoid. And on the left hand side, the one extreme position, the bonds are moving upwards. The other one where the bonds are moving downwards, the bond angle is changing. So ellipsoid इधर वाला और इधर वाला दोनों एक जैसा है. मतलब if you are moving left to right, there is no change in the polarizability. So d alpha by dq is 0 here. So not active. It is not active, Raman active. The third one is the asymmetric stretching. Again, this is the mean position. Then you stretch it along this direction. The bond length increases, increased length. So while the other one is getting compressed. So overall, the polarizability change is represented by this ellipsoid on the left hand side, and then when the reverse thing happens, the bond which was elongated now getting compressed, the other side it is getting elongated. So this is again the shape of ellipsoid on the left hand side and right hand side is the same shape and size. So change on this side is same. So when you draw these alpha versus q or alpha versus xi, here it is shown. So आपको ये d alpha by dq again it is 0, coming out to be 0. शेप देख के आप समझ सकते हो. पहला वाला एक्टिव क्यों था? जैसे ही आप इधर वाला चेंज इज डिफरेंट, इधर का चेंज अलग है. लेफ्ट साइड राइट साइड it is not the equal change. So this was active when you plot. So that means when you're taking the difference of coordinates and the difference in the alpha polarizability change, that is different on for the stretched and compressed condition. This one, the change was similar on the left and right side when you two extreme. So what we are doing, we are taking the mean position, एक एक्सट्रीम पोजीशन, दूसरा एक्सट्रीम पोजीशन जो ड्यूरिंग द वाइब्रेशन आ रहा है उसका एलिप्सॉइड ड्रॉ करना है. और अगर दोनों साइड चेंज एक कंसिस्टेंट चेंज लेफ्ट टू राइट आता है तो रमन एक्टिव होगा. अगर वो चेंज इक्वल है दोनों साइड में मीन पोजीशन के करस्पॉन्डिंग, अगर आप दो एक्सट्रीम पोजीशन पे करते हैं तो यू कैन एक्सपेक्ट दैट डी अल्फा बाई डी क्यू विल बी 0 एंड इट वॉन्ट बी रमन एक्टिव. ठीक है. So this is the two things that you can see. Asymmetric stretching, the mean position, look at the left and right side of the two extreme positions during the vibration, asymmetric stretching vibration. The changes are same, exactly the same. So d alpha by dq will be 0 on this. So the net result is that symmetric stretching is Raman active. You can see only one spectrum in Raman. When you perform Raman spectrum on CO2, you get only one peak. When you perform infrared spectroscopy on CO2, you get two peaks. How? So this is your so stretching one is symmetric stretching, which is Raman active, highly intense, and this one. So you look at the scale first. X-axis 4000 cm inverse and 20 cm inverse. So it is conventionally we follow the same thing. जैसे कि आप UV visible spectroscopy करते हैं, shorter wavelength to longer wavelength जाता है, मतलब high energy to low energy आपका spectrum चलता है. तो यहाँ पे भी आप देख रहे हैं 4000 cm inverse to 0. तो x axis पे ऐसे रखा गया. जब भी हम infrared spectroscopy करते हैं तो ऐसे scale x axis का define करते हैं. higher energy to lower energy side. ठीक है. सो इसीलिए ये 4000 cm inverse आपको यहाँ पे दिख रहा है और इधर 0 दिख रहा है. Then what you see here, yes, the upper part is the infrared spectrum which shows asymmetric stretching, highest energy very intense, and this is the bending. Bending mode is degenerate, so they appear at the same energy. That one is out of the plane, one is in the plane of the screen. So this is by observation, by experiments, it has been found that for molecules with a center of symmetry, no IR active transition are Raman active, and vice versa. So that is for such symmetric molecules with having center of symmetry, IR active vibration are not Raman active, and Raman active vibration are not IR active. So CO2, you always have a very intense Raman line in symmetric vibration. If you talking symmetric vibrations, क्योंकि symmetric vibration में जैसे कि CO2 में दोनों बॉन्ड एक साथ स्ट्रेच हो रहा है, तो पोलराइजेबिलिटी बहुत ज़्यादा चेंज हो जाएगी. There is greater change in the molecular volume. Symmetric vibrations, large change. So सबसे आसान तरीका है पकड़ने का कि रमन एक्टिव होगा कि नहीं. If you clearly see there is a large change in molecular volume, ठीक है, मॉलिक्यूल का वॉल्यूम सबसे ज़्यादा चेंज हो रहा है जब वो स्ट्रेच हो रहा है या कंप्रेस हो जा रहा है एकदम से इक्वली ऑन बोथ साइड्स. तो ऐसे केस में इलेक्ट्रॉन्स आर मोर स्प्रेड आउट. इलेक्ट्रॉन क्लाउड इज स्प्रेड आउट. ये थोड़ा फैल जाता है. इलेक्ट्रॉन क्लाउड इज मोर स्प्रेड आउट, लेस tightly held by nucleus, easy to distort. So this will be easy to deform, distort. So you can bring about distortion easily. So we say high polarizability. So suppose it is under, when you are stretching it, we are talking about the stretched condition. When it is symmetric stretching, high polarization, that will give rise to high polarizability. And in the same way, when it is compressed equally, contracted on both sides, so you can think of, there will be greater reduction in the molecular volume. Electron cloud will be confined to a smaller volume, very small space. So they will be tightly, the distance with the nucleus will be less, they will be more tightly held and less polarizability. Reverse case we can imagine. So maximum change in the polarizability will be obtained in a symmetric vibration. These are also called breathing vibration. जैसे lung contract करता है, expand करता है equally without change in size, without change in shape. So that is what happens in a perfect symmetric vibrations when we are talking about symmetric stretching mode. So these are also called breathing vibrations, and all these breathing vibrations are very intense. बहुत शार्प, बहुत इंटेंसिटी काफ़ी ज़्यादा आएगी स्पेक्ट्रम जब भी आप स्पेक्ट्रोस्कोपी परफॉर्म करेंगे. सो दिस इज what we know about. हाँ, so this is a generalization of the observed trends. देखिए, ये कोई रीज़न नहीं है. म्यूचुअल एक्सक्लूजन इज नॉट अ रीज़न, इट इज़ ओनली अ जनरलाइजेशन ऑफ ट्रेंड. द रीज़न इज what I have just discussed. In case of CO2, we can see that there are the polarizability. When we see step by step how the polarizability changes, by drawing the ellipsoid, we find that d alpha by dq, the slope comes out to be 0. Okay, in the two cases, while only in one case, when we have symmetric stretching mode, it is having a non-zero value, the d alpha by dq, the polarizability. So because of this reason, it is Raman active and other two are not. But the generalization of the trend of such molecules helps us in identifying the geometry of the molecule. on verifying the structure of the molecule. So this is what Raman active. So if a molecule, if you observe the IR spectra and Raman spectra of a molecule, if you find that the modes that are IR active are not seen in the Raman spectra, and what you see in Raman spectrum you do not see in IR, that means you are having a center of symmetry in the molecule. So it is, so that gives a very good uh, indication of the structure, and then you can build up from there. So बहुत बड़ा hint हो जाता है जब भी ऐसा ऑब्जर्वेशन कुछ हमें मिलता है. For spherical top molecules, um, the okay, so this is an example of CH4 tetrahedral methane, you can see, and the polarizability ellipsoid will be appear like a perfect sphere, spherical. So it has a spherical polarizability ellipsoid. So in any direction you apply electric field, it has same polarizability. So why we call it this? You apply electric field in this direction, same, किसी भी direction, any arbitrary direction you take electric field, same change in polarizability. So in any direction, so that's why the same change in polarizability will be there when you apply electric field in any of the directions, and that's why we call it draw it like this, polarizability ellipsoid. And okay, so just to further visualize what is happening here, we in case of CO2 and the other things, we can return to this, choose another molecule, and so this was carbon dioxide. So we were talking about symmetric stretching mode. देखिए symmetric stretching mode, polarizability change in polarizability, it has graph like this, polarizability versus Q, whereas the dipole moment has a no change. See the two contrasting pictures on left and right, polarizability versus the Q, change in coordinates, dipole moment versus Q. You can clearly see there is no change in dipole moment when it is stretching symmetrically, stretching, compressing, and dp, where in case of polarizability alpha plotted on versus Q, d alpha is positive slope. Similarly in other cases, this is the bending mode, the polarizability, look at the polarizability change, d alpha by dq is 0, however there is change in the dipole moment, this is a positive slope now. So this is mode is Raman inactive but IR active. So this is what you can see. Then the final one, this is your asymmetric stretching. Again the change in polarizability, look at this how it changes, and close to the equilibrium position when you draw this slope here, in case of polarizability it is, you are getting 0, it is flat over the near the mean position. Whereas if you look at the dipole moment, it is following a, giving you a positive slope. So IR active but not on. So this is your basic reason. However, the generalization of the trend does help you in deducing the structure of a molecule when you have both the Raman and IR spectra, and if there is, it follows a mutual exclusion principle, that is जो इसमें एक्टिव है IR में वो रमन में नहीं है, जो रमन में है वो IR में नहीं है, तो आप क्लियरली कंफर्म हो जाते हैं इसकी सेंटर ऑफ सिमेट्री होगा. ठीक है. So this is how we understand the, so H2O and CO2, this is the basic models through which we can understand the spectroscopy very well. For in case of water, all the three modes were IR active and Raman active. There was no center of symmetry. In case of CO2, there is center of symmetry, and the modes which are it follows the mutual exclusion principle. IR active modes are Raman inactive and vice versa. That's we have just seen. Okay, back to what we were discussing for spherical rotors, spherical top molecules. So taking example of CH4. This is the ellipsoid, and we'll discuss more about this. But first, let me tell you, there's one more thing that happens in Raman. रमन स्पेक्ट्रोस्कोपी में ऐसा भी देखा गया है कि जो रमन स्कैटरिंग होती है उसमें sometimes it may happen that some of those scattered signals, scattered जो photons है वो polarized रहता है. अब ये that is the oscillation of electric field vectors is contained in a plane or in something like that happens. So polarization क्या होता है वो आप जानते हैं. Polarization of light, you are familiar with that. Organic में भी पढ़ा होगा आपने, 11th में भी, physics में भी पढ़ा होगा. So this is what we mean. In a normal, when you are looking at light में क्या है? Look at the oscillation of electric field vectors. So this is randomly in all directions, right? But when you apply a filter, polarizing filter, so kind of a so when you apply this polarizer, you place a polarizer, what happens? एक particular direction में, which is the axis of the crystal, polarizing crystal, इसके उसके along vibration रहेगा और बाकी सब खत्म हो जाएगा जो लाइट की. So जब लाइट इसके थ्रू पास करती है, only in one direction as shown in the red color, बस वही बचता है, बाकी सारा ब्लैक वाला खत्म. So there is no oscillation of electric field in other direction, and only the one which has oscillations along the axis of the crystal, they are retained. Okay, so this is your plain polarized light, जो normal आप polarized light कहते हैं. So this is unpolarized light. Example यहाँ पे देख रहे हैं, oscillations अलग अलग plane में है. Okay, so but when it is passing through the polarizing filter, it is only the yellow one is retained, polarized light. So ये आपका meaning है polarization का. So light source pass through polarizing filter, and this is, so earlier if it was having, for the sake of simplicity, only two direction has been shown here, blue and yellow. So इस डायरेक्शन में भी ऑसिलेशन हो रहा था ब्लू वाले में ऊपर नीचे, और इस वाले में भी, येलो वाले में भी. तो जब फिल्टर से पास किया तो ओनली the one that is having direction parallel to this crystallizing filter, polarizing filter के क्रिस्टल में एक्सिस जो थी उसके पैरेलल वो वाला रह गया, बाकी सारा एक्सक्लूड हो गया. So this kind of thing is polarization. plain polarized light कहते हैं, जो लास्ट में जो लाइट निकल के आती है उस polarizing crystal से, उसको हम plain polarized light कहते हैं, right? So this is natural light polarizer. अब कुछ polarization हो गया है, इसको कैसे पता करते हैं? वैसा ही एक और क्रिस्टल रखते हैं जिसको कि हम एनालाइजर कहते हैं. ओके, सो दैट इज पोलराइजर एनालाइजर को दोनों को रखने पे ही आपको पता चलेगा कि सच में पोलराइज हो गई है लाइट. सो इफ यहाँ पे देखिए, दिस इज द एक्सिस ऑफ द पोलराइजर, एक्सिस, and this is the axis of the analyzer. So and the two axes make an angle of theta. This is what has been shown. So ऐसे केस में जो अगर if theta is 0, पूरा का पूरा परफेक्ट जो मतलब all the intensity of light is maximum. If theta is 0 in this case, maximum intensity would be there. and as you change the theta, the relative intensity of the light that has been polarized, वो polarized light का intensity कम होता जाता है. और when if the same thing, if theta is 90 degree, तो अगर perfectly polarization हो गया है तो zero intensity, no light will pass, क्योंकि अब उस डायरेक्शन में उसका कोई कंपोनेंट बचा ही नहीं है जो there is no component lying along with the axis of analyzer. So in that case, so this is the thing that checks how do you check the polarization has happened. So that is the statement over here given in this case. So theta is the angle between the axis of polarizer and analyzer. If both are parallel and the light has been plane polarized, then you will get maximum intensity when both are parallel. Theta is 0. At any other given angle, the intensity will reduce, and that will be given as E naught cos theta. So it will pass through without reduction only if polarized axis of two prisms are parallel to each other. So दो जो prism था जिसका axis एक जैसे align हो रहा था, उस केस में sorry, it is prisms, then the maximum intensity is observed. At any other orientation, the intensity pass will decrease until no light is passed when they are perpendicular. So perpendicular केस में 0, पैरेलल में मैक्सिमम इंटेंसिटी. अब इन दोनों को कंपैरिजन से आपको डिग्री ऑफ डीपोलराइजेशन डिफाइन करते हैं, दैट इज ऑब्टेन्ड. ओके, सो वी so in case of complete polarization, there will be no light passed when it is perpendicular. The analyzer is perpendicular to polarizer. There will be maximum light that will pass through when the angle between the two is 0. और बीच के किसी भी एंगल पे वो रिलेटिवली घटता जाएगा, ठीक है. और फाइनल सो मैक्सिमम टू 0, 90 डिग्री 0 डिग्री पे मैक्सिमम, और जैसे जैसे 90 की तरफ जाएंगे घटते घटते 0 हो जाएगा. ओके, and then you have now suppose, अब second thought, अब second thing, अभी हमने imagine ये जो discuss किया, depending on assuming that the light has been completely polarized, कि कोई भी oscillation दूसरे direction में नहीं है, just along the axis ही है. लेकिन ऐसा भी हो सकता है कि जो light polarize हो रही है वो completely polarized नहीं है. पोलराइज हुआ है मतलब एक पर्टिकुलर डायरेक्शन में मैक्सिमम इंटेंसिटी होगा, लेकिन दूसरे डायरेक्शन में भी कुछ ऑसिलेशन इलेक्ट्रिक फील्ड वाला होगा जो कि कम होगा. तो वैसे केस में आपको जब 90 डिग्री का इसको रोटेट करेंगे, सो इफ द लाइट इज नॉट कंप्लीटली पोलराइज्ड, or we say that it is partially polarized. If it is partially polarized, मतलब intensity एक most of the oscillations are in particular direction, but in other direction has some small oscillations are also happening. Light is passing, जो light pass कर रही है उसमें कुछ उसका इलेक्ट्रिक फील्ड का कंपोनेंट दूसरे डायरेक्शन में भी ऑसिलेट कर रहा है लेकिन कम है, they are not in majority, there is minor thing. So in such case, so in the second case what will happen, there will be, if it is not, if there is only partial polarization, when theta is 0, maximum intensity, when theta is, अब धीरे धीरे उसको रोटेट कर रहे हैं, 90 डिग्री होगा, एनालाइजर पोलराइजर का मिनिमम इंटेंसिटी हो जाएगा, ठीक है. बट इट विल नॉट बी 0, कभी भी 0 नहीं. अगर पार्शियल पोलराइजेशन के केस में 90 डिग्री पे मिनिमम इंटेंसिटी होगा लेकिन 0 नहीं होगा, क्योंकि अदर डायरेक्शन में भी बहुत स्मॉल थोड़ा सा ऑसिलेट इलेक्ट्रिक फील्ड है जो ऑसिलेट कर रहा है उस रेडिएशन में. So this kind of situation will also arise in case of molecules. So now we turn to our focus to what happens in Raman. Some of the scattered light gets polarized, and then we calculate the depolarization ratio. Okay, so ये एक बहुत अजीब सी चीज होती है पोलराइजेशन. Raman scattered light is polarized. How? What happens? So this is what I just discussed. Only partially polarized. If the light is partially polarized, majority will be electric field vectors will be parallel to the plane, but some of them are also in other orientation. So intensity will not go to zero when they are polarizer and analyzer are perpendicular, but it will only become minimum at a point. So now following this discussion, we can define a phenomenon. We define a scheme for measuring this polarization or depolarization. So we call it degree of depolarization rho, indicated by rho. So intensity when the theta is perpendicular, that is theta is 90 degree, and when theta is 0, that is theta 90 degree and when theta is 0. So इन दोनों को कंपेयर करते हैं, perpendicular by parallel. Look at the light, how much light you are getting. So अगर polarization नहीं हुआ है, imagine there is no polarization happened. In that case parallel करो perpendicular, दोनों केस में same intensity होगा. If no polarization, then the intensity of light will be same. If there is polarization, perfect polarization, 100% polarization, the intensity of perpendicular will be 0, and the value of, so this will fluctuate from 1 to 0. This degree of depolarization, the way we have defined, it will vary between 1 and 0. So let's go to the next. So this depolarization ratio, in case of complete polarization it should be 0. In case of partial polarization it will be, in case of any no polarization it will be 1. So let's define it this way. Perfect completely plane polarized light, degree of depolarization will be 0 because I perpendicular is 0. For completely unpolarized light, degree of depolarization will be 1 because whether it's perpendicular or parallel arrangement of the analyzer polarizer, intensity is same. So for any intermediate values of polarization, the value will lie between 0 and 1. So Raman signals, why we are discussing this polarization? Because the Raman signals of some of the molecules have been found to be plane polarized, even though the exciting laser is not completely polarized. ओके कंप्लीट लाइट इज कम्प्लीटली अनपोलराइज लाइट में, मतलब जो अनपोलराइज लाइट आपने यूज किया और जो स्कैटरिंग आप ऑब्जर्व कर रहे हैं उसमें कुछ सिग्नल्स पोलराइजेशन दे रहे हैं, पोलराइज लाइट दे रहे हैं. सो दैट वाज सरप्राइजिंग एंड yeah, so this is the discussion that we have to follow. So we'll do it in the next class. We'll follow from here the polarized Raman lines and how do we analyze it, what are the implications of this observing certain, if Raman polarized lines are observed. So we'll see it in the next class. Okay.